All right, Professor Brian here. Another installment of Workout Wednesday. Today we're going to be working over Chapter 6 stuff, which is electronic structure of atoms. The first question that we're going to look at is out of the text, actually. When we take a look here, it's going to be 6.34, which speaks about energy, frequency, and wavelength, as well as the photoelectric effect and kinetic energy. So we're going to tackle all of these. Also, you notice I have pulled up the formula chart here that you have for your reference material, and make sure that we are aware of which one of these formulas to use in each scenario, and then we're going to do the calculation. So the first part of the question says titanium metal requires a photon, so we're talking about a single photon, with a minimum energy 6.94 times 10 to the negative 19 joules. So that is our threshold energy. What is the minimum frequency of light necessary to emit electrons via the photoelectric effect? So the photoelectric effect, we remember, means that we have to have enough energy to kick off and emit an electron from the titanium metal. So we need to do some calculations to figure out A. So A wants us to determine frequency of light. So over here, A, we are looking for nu. We have energy, 6.94 times 10 to the negative 19 joules. And the relationship between energy and frequency, we should know from our equation. E equals h nu is here. So utilizing that equation, we get E equals h nu, and to solve for nu, we see that nu equals E over h, and if we put this in, 6.94 times 10 to the negative 19 joules, h is a constant, 6.63 times 10 to the negative 34 joule seconds. We end up with an frequency of 1.05 times 10 to the 15, and our units of interest are seconds to the negative 1. Remember, frequency is always in seconds to the negative 1 or hertz. So this is the minimum frequency necessary. So let's take a look back. Part B. So part B asks, what is the wavelength of this light? Well, we can relate frequency to wavelength utilizing, we're looking for wavelength. We can relate frequency to wavelength by C equals lambda nu. We know nu. We know C is a constant, so to solve for lambda is equal to the speed of light over the frequency, which is equal to 3 times 10 to the 8 meters seconds to the negative 1, all over frequency, which we have here, 1.05 times 10 to the 15 seconds to the negative 1. Plug this in the calculator. We end up with 2.87 times 10 to the negative 7 meters, because seconds to negative 1 cancels. Left with meters. Right, this is also equal to 287 nanometers. All right, part C asks us, is it possible to eject electrons from titanium with visible light? So if we remember and take a look at our electromagnetic spectrum, I'm going to pull one up real quick. You take a look at our electromagnetic spectrum here, we see that the end of the visible spectrum ends with violet, and it stops around 400. Our wavelength that we just calculated is 287. So 287 is smaller than 400. Therefore, it will exist in the UV range and not in the visible range. So the question asks us, what is it possible to eject them from visible light? And we have to say no. Now, we also need to be able to explain the why. And the why is because visible light has a longer wavelength and lower energy than needed. So we are not dealing with enough energy. We have not met our threshold energy in the visible spectrum. Okay, now let's look at part D. Part D is asking us about the maximum kinetic energy of emitted electrons given a wavelength of 233, which is smaller than the wavelength of 287 that we calculated. So part D asks us 233 nanometers. So D is where we need to use our equation. E for kinetic energy is equal to h nu minus the work function. And remember, h nu is the incoming and work function is the threshold energy. All right, so what is phi equal to? Phi is equal to the energy at the very beginning. We were given that energy, 6.94 times 10 to the negative 19. And h nu, remember, can also be shown as hc over lambda minus phi. And to know lambda, we were given lambda in the question, 233, which is equal to 2.33 times 10 to the negative 7 meters. So we need to plug this lambda in this equation, plug this work function in this equation, and we can answer our question. EK is equal to 6.63 times 10 to the negative 34 joule seconds times 3 times 10 to the 8 meters per second to the negative 1 all over 2.33 times 10 to the negative 7 meters. If we put that in the calculator, we end up with joules. Seconds gone, meters gone, meters gone. And that is equal to 8.53 times 10 to the negative 19 joules. And there's our answer. Okay, and notice that this is a larger energy than our threshold energy. Slightly larger, but larger. And we get that because we are throwing at it a more energetic photon with a shorter wavelength. Okay, and the last question on this question, last part of this question, says that what is the maximum number of electrons? It looks like a typo, it should be E. What is the maximum number of electrons? So now we're no longer talking about singular electrons, we're talking about maximum number of electrons that can be freed by a burst of light whose total energy is 2.00 microjoules. So we want the maximum number of electrons. So if we know that the burst of light is 2.00 microjoules, and we know the threshold energy, we can count the number of photons by a simple calculation. So that last part, which it should be part E, or D number 2, is giving us a total energy equal to 2.00 microjoules. We know our threshold energy, 6.94 10 to the 19. (6.94 times 10 to the negative 19 joules. And remember, we don't write the unit very often, but this is per photon. So to get the number of photons in this many joules, what do we need to do? We need to divide this value by this value, but we need to have similar units. So to get the number of photons is equal to 2.00 times 10 to the negative 6 joules. Remember, this is the micro prefix, 10 to the negative 6, all over 6.94 times 10 to the negative 19 joules per photon. And that will give us number of photons calculated. (2.88 times 10 to the 12 photons). And remember, photons are singular electrons, same thing, photons, electrons. And here is the number. This is a lot of photons that are ejected. So hopefully we've got everything together on that. I'm going to show this front page again and zoom out for you. And if you have any questions, feel free to send me an email. All right.